Okay. Also send it to other servers.
Now it should work.
Yes.
Also, yeah, but let me check the YouTube that is working because Alex changed something again on the recording thing and doesn't.
Now I'm seeing yeah, OBS. Oh, it's now I'm seeing Discord, yeah.
Okay, it works. Now it's
So I wonder if it's possible to make the stream a bit more high quality.
Oh.
In terms of make the thing bigger.
Oh, you mean this thing
stream.
here. I think it's maybe that's a Discord thing. I remember it was possible, but about the stream.
Yeah, I think it's hard to read the text.
Let me. Yeah, that's more a problem with my.
Both streams, stream as a... Huh.
Stream.
Like I would maybe.
No, wait, what?
Oh, I see. Yeah. I would maybe make the whole screen bigger and just like.
Like you can do this. No. I can
think
remember you
OBS could
could
also...
do that, but I don't remember how.
if you click on the plus thing on when you open the stream, there's a plus that's zooming in. Yeah, it's.
I mean, I can zoom in, but that doesn't make it, a bigger percent of the screen. Right? That just does that.
Stop watching stream when you pop out. You can click on pop out stream. Click with right click and pop out stream on the stream, and that can make it bigger.
I think I need to return to Discord and go to here.
Right click and pop out stream should make it.
Where was it? I did see it earlier, but I don't remember.
If you click with right click on the stream, and there should be more options. Pop out stream. Oh, okay. Maybe that's only on. That's maybe only on Windows or something then.
Or only on the app, because this is the browser.
Or the app, yeah.
I remember you could do that, but I don't know how to do it now on the current. Like you can pop out this, but it pops out the whole thing, right? With the
Another option is kind of like taking the whole browser thing and just stretching it, just putting it outside, stretching the whole browser window, basically.
I don't think I can easily do that.
I mean, like the whole not sure what browser that is, Chrome or like taking it at the very top and just manually stretching it a lot.
Like
moving it to the side and stretching.
Yeah, I can stretch it more than this, I think.
Okay, I see Windows is also limiting this.
Anyway, I think it kind of works. I think we can leave it like this, and I'll try to figure out another day outside of the reading group how to do it.
Yeah. Like, I think you could now at least like zoom it a bit. I think that at least.
Like, why does it do this too? It's really annoying.
Oh, it's slightly more readable. I think you made it bigger somehow.
No, I did do that, but now it's you're seeing it with the delay. I mess up. I have to. Oh.
That was good how it was stretched. That was readable, what you did before.
Why does it do that? Why clicking on the thing does makes it? It's going too hard to put it. Okay, so I'll leave it like this and I'll try another day to. Yeah, I do remember you could put it at wide screen, like with the stream being the whole screen, and it's something like with pop out. But I don't.
Yeah, that's
I don't
possible.
know how
In
to
the
do
app,
it on
probably.
the current version of Discord. It used to be like you can pop out
Yeah,
the
I
thing.
have the pop. Yeah, I have the pop out thing. Maybe you would have to install the app, and that would allow it.
Like you can do pop out, but it pop outs also with with the other people on the bottom.
I see.
And that takes space, and yeah, that's the problem. Anyway, let's get to the actual paper. Oh, sorry,
Okay.
this is not this one. So
Yeah, you can also zoom on here, on your own Windows or
yeah,
Linux.
yeah.
That instantly makes it more readable on the stream.
Recent work has shown that I mean, it's not that it's that important for it to be readable on the stream, where people can actually just open the paper themselves. But yeah.
Yeah, that as well.
I didn't sleep very well today. Anyway, recent work has shown that the computations transformers can be simulated in the RASP family of programming languages. These findings have enabled improved understanding of the expressive capacity and generalization abilities of transformers. In particular, yeah, so RASP programs is like, so RASP is this thing from this other paper, but I'm not sure if it already existed before this, but they made a compiler that compiles RASP into the weights of a transformer in this Google paper some time ago, years ago now, where RASP, what was the, it's restricted access sequence processing language. Yeah. The variable sequence operations and selectors. We'll see how much this paper explains that. If it doesn't explain much, we can go back to the original paper to
Yeah.
see that. Yeah.
Also, if anyone else has any comments about this paper and so on, feel free. We can be as interactive as possible.
Yeah. Particular the RASP language.
Oh yeah, when you zoomed in on your own machine, it's instantly readable on the stream, so that's good.
I think I started to get sick today, but
Okay.
Anyway.
Length generalize. What is length generalization?
Ah.
It's like a length of like addition, for example. How long are they? The numbers.
Carrier is RASP like computation, but they don't show that training models do so and are interpreted right. Okay, because yeah, RASP style computations are a subset of what transformers can do.
Mm-hmm.
I mean, you can I think do anything with RAS style computations, but it's a different, the kind of programming paradigm you're piling with.
Mm-hmm.
Interpretable methods. Yeah. So I'm not reading as much aloud because I'm a bit sick, but I don't want to. Yeah. But let me just want me to mention something. This happens. Okay, so they are thinking. I guess they are more. They are not trying a thing where they. I am sure if they will take arbitrary things and turn into trust programs. They are thinking that there is a set of things that transformers could do that are equivalent to some simple RAS program, and they want to find a way of extracting that.
Mm-hmm.
I think.
Fully reparameterize a transformer as a RAS program, and then apply causal interventions to discover a small sufficient subprogram. I guess it's similar like
Project encoders.
no, like in this context, like in the original Grokky module edition paper, like you have the trigonometric algorithm that if you delete that, you delete a lot of the explained variants. So I guess similar here, you have a RAS program, which is some algorithm. I'm not sure what exactly are what all programs are defined as RAS programs. So like one program could be the trigonometric algorithm, for example. I'm not sure if that's a type of RAS program. I don't know what the RAS program is. I guess that's how I see it now. Let's see.
I think you might be able to write this at a RAS program, but it might be a weird way of doing it that doesn't show you the.
Okay.
We'll see. RAS. Also,
With this length generalizing transformers. Okay. Let's see.
I think that the Lang generalizations conjecture may be important for some reason.
Informed. Okay. I see. Oh, there are also dialects of the RASP language.
yeah,
And the RASP language is 5 years old. Okay. I see. Length generalizing. Okay. Simple programs are more robustly generalizing. Occam's razor. Hmm.
Anyway.
Like they mention some interpretable methods that they recover circuits that are tied to specific input lengths and input templates and so on. But like how are the working paper? That's kinda for all inputs an algorithm.
Doesn't generalize or
Yeah, it's true that it's only for a particular modulo, for example. Okay.
I just into a thing where you put a longer context with more numbers, it will generalize.
Okay.
Once I generalize, so the small separate set an algorithm of formal language methods. On models that let's generalize. Huh. Non-program like mechanisms.
Yeah, I'm not sure, but like, the RASP program is like something that would work with like all inputs instead of like, a circuit would work for like a particular type of input, but like a RASP program would work like, for all kind of input somehow.
I think it depends
I
on
see.
the input, so on the circuit and all that, but yeah.
Yeah.
The compile RASP. Selectors aggregation elements adapted the also it seems like the oh yeah, RASP
Under
is
a linearization assumption for a layer normalization, so no non-linear normalizations. Layer norm. Okay. The naive program is exponentially large in depth. Like, I kind of have this tangent thought here. Like in physics, there's like effective. I think it's called effective theories. I'm not sure if it's effective theories. There's like some class of theories that start with simplification and then they correct by adding more and more terms to predict something, to approximate something. I wonder how similar it is to this. Is it effective theories?
So let's try to understand the definition maybe of the RASP word.
Yes.
Like this activation variable is like a matrix, D by N matrix, where D is specific to the variable. So that's just analogous to like the activations from all the tokens, the input tokens, I guess. some embedding.
Selectors aggregation, element-wise operations. Okay, I'm just starting to go over the definition now.
Yeah, I mean so the compiling programs typical values for the variable might be different code information. Okay, information. Huh. Even
Right. So activation variable is like embedding. N is the input size, so it's D by N. And selector variable is like attention matrix. It's N by N.
okay, so makes sense. So that's center values are like probably trying to do what show what attention is doing. Or code this kind of thing attention to. Two initial variables correspond hunters for precision tokens. Oh yeah, position. This is the positional encoding. I understand.
Yeah, one hot encoding, I guess. Yeah.
Okay, I compare. Attention measures set operators.
Is that Python notation? I think so. The dot for VI. Okay.
I don't know which one you mean, but probably.
Yeah.
I think that's just the ith column.
Yes.
Obviously, this Python notation is superior than whatever mathematicians use.
Yeah.
But this notation is confusing. The selector is an operator. It's in R n by n, R to the n by n. And alpha equals select, k equals vk, q equals vq, op equals a. And equals select, k equals vk, op equals b. Evaluating the tensor. Alpha, yes, a vqi transpose a vqs.
I haven't gotten there yet. Is that Knocker Delta? Interesting that they use Knocker Delta.
What's Knocker Delta?
The position equals I'm not sure what's the Greek symbol. Yeah, delta. It's called Knocker Delta. So the delta JI, the definition of position IJ. Do you know the definition of that symbol? I think that's the symbol that they're using. Yeah, this thing.
Yes.
Yeah, it's 1 if j equals I, and it's 0 otherwise. If j doesn't equals I. So it's like, yeah. I know that exists from classical mechanics.
So that's just a nice, yeah, that's just the position, which position it is on.
Yeah, it's position IJ. Yeah, if I equals j, it's 1, otherwise it's 0. Oh yeah. Identity matrix for I, and I think that's identity matrix, right? With j equals I.
Identity. But the thing is, it's not might not be a square matrix. So it's T by N. It might be rectangular matrix. I guess that's also identity.
This shouldn't be. It's probably indication function inversion bracket. They're using lots of fancy math stuff here, I see. I think so.
It's a kind of paper you like.
Would that make sense? Yes. I like it when it's possible to connect it with other disciplines. Yeah. Okay. I think. Oh, it's just. Oh, it's like generalized Knocker Delta, where it's 1 when the condition is true. It's 0 if the condition is false, right? Yeah. So it's like, if condition in math, I mean in programming.
I feel like this is a lot of math, and I will understand much faster if there was like some simple documentation of how RAS operations work or something.
Do they? I think yeah. Later, I'm waiting for examples of these things. This is a very okay. I mean, yeah, I like the fact how they write it in all those fancy math things. But yeah. So position is like this. Token is. If the first thing if the J symbol from the alphabet equals the xi. In this context, xi is just a vector from transformer. Or no, input string. They write it later. Okay. Alphabet to nth. Okay. So the alphabet with to the power of n. Does that mean like the size is n, or is that some? I know in category theory there's some different meaning to this. What does it mean here, for instance?
It's just
it's
Cartesian.
like set. Okay, Cartesian. Okay. Right, I see. All strings of the length n over the alphabet. Sum. It's not sum. I forgot the word for this symbol. Sigma. Yeah. Okay, so x. Okay, Cartesian. Yeah, right. Makes sense. XI is just from the alphabet, alright. So if the... Huh? But aren't the... So if the... Kind of confused by the definition. If a symbol from the alphabet is equal to another symbol from the alphabet, can the I...
Right. So I guess the embedding is like it's just one hot embedding, right? You take the vocabulary size, and then for each token you put a 1.
Yeah, on the position encoding is the same kind of thing.
Yeah.
Okay.
Okay, so that's it.
Jth component of the vector at position.
They do arbitrary function for element-wise operations, but don't the MLPs like they are more restricted than that? I guess it doesn't matter if RASP can do more things that the MLPs can do because you only want to decompile it. But how does there are things that you can't do on a single MLP, right?
Yeah, that's true.
I wonder how they solve that on if they do the same kind of thing or no, it's not there. They use a different restricted version on Tracer. Or maybe I'm missing something. But yeah, never mind.
I'll get there later.
Yeah. But I guess this aggregate operator, do you understand this selector operator? This they're doing like V transpose AV. A is like some arbitrary matrix, I guess.
I mean, this is the like the same as taking the BQ weights, you know, on the transformer circuits, like mathematical formula framework paper, right? They have some
Okay.
like the
So-
A is here, like a matrix, like there will be the thing that gets multiplied by the K and query. Isn't it just like this, literally the same as attention, but in a different notation, maybe? Not sure. I'm asking because I don't. So
Yeah, looks like. So A is like QK transpose.
yeah.
Yeah.
Like the weights, right? Where BQ and BK is like the activations.
Value matrix. Oh no. Okay. I see.
Right?
Yeah.
Like that's why this is a variables and this is like the operator because the operator is the weights.
I see. Okay, makes sense. Okay.
The thing is, on the MLP, they treat the MLP as doing arbitrary function, right?
Yeah.
But the MLP can only do arbitrary, like some matrix multiplication RLU. So I guess.
Approximation theorem. You can approximate any continuous Lipschitz
Yeah,
continuous
but
function.
with more layer, right? Or can you do it
Okay,
with
I
a
see.
single layer, infinite width?
That's true.
So token is the input embeddings position as well. One hot encodings of the input. Select should be the attention logits. Aggregate should be the softmax attention and value projection. Yeah, it seems as a language for the different parts of the transformer. Okay, I see now. Saving.
Right. So anyway. I'm not talking that much today. Okay, that's fine. Anyway, so
Okay.
what do you say?
Self-attention captured using select and agree operators. Activation rebus.
Sample. Okay, they have some samples here, by the way.
Oh, okay. Yes.
Like the a select can be the identity matrix.
Mm-hmm.
So it's whether k equals q. K equals q minus 1. Like, I think I kind of understand how it works. Like it's just a fancy way of writing as programs the model. But of course, the actual model, like if you describe it fully this way, is going to be a giant pile of RASP operations, right?
Mm-hmm.
They're trying to find. I'm curious what they do to filter that and all that, because I mean, you could, the way it's written, you could just write the transformer as itself, like it's just a select operation that's literally the weight of the transformer, and
Mm-hmm.
the like and the function, you do whatever function the MLP is doing, and that's it. You just rewrote the transformer minus maybe the because you could roll the layer norm in the function in a very weird format. But I think the idea is to pick circuits and describe them with these operations.
Hmm.
Yeah.
Instead of fully taking the model and converting it into this, which is kind of, I mean, you could try to decompose the model as a bunch of smaller RASP operations instead of a really big one that's just the whole model. But on its own, the RASP doesn't, do the decomposition, but it's just a way of expressing the operations. In the compression, okay. Program for finding the most frequent character in a string. This is for a haircut performer. Wait, I'm confused because here they mention that the RAS differs from other RAS dialects in using softmax for aggregation. Where does that? Where is that explained? What?
There is softmax mentioned right above the primitives, where yeah, there's the, I forgot the symbol. Phi, I think it's phi. Yeah.
Oh.
The prediction equals phi. Prediction J equals phi at the bottom.
Okay, I was missing this part. Okay, so they just had a prediction is softmax of
So yeah, apparently like RASP used hardmax, and this one is using softmax.
Okay.
I see.
Oh no, it's over there. Right, so there is a bunch of RAS variants. Okay, the comparative machine. I think this is the interesting part, maybe. The parameterization is simplification. The first part. Okay, simplifies the program. So this is the kind of thing where the same kind of thing as doing, trying to use a sparse encoder on the model or something, and then doing circuit search on that. It's just a way of dividing the model in a way where your ablations might be better than doing them on neurons or whatever. Anyway. Linear layer normal solution. If each layer normal operation can be replaced by a linear operation for some constant parameter. Okay, this is kind of weird. Okay, so normally the layer norm is not linear, right?
Yeah.
But they are doing a weird thing where they fine tune transformers because there's some other paper that shows you can fine tune them to not, to be linear, to make the layer norm equivalent to linear, and that works apparently. That seems really weird to me, but okay. Is there some reason?
Recently, I went on some rabbit hole of like all the non-linearities. Apparently, that's true that there are ways to change the layer or to make it lighter or something like this. I've just seen it as a footnote, so I don't know.
I'm confused why they did this instead of adding something for that on the on the DRASP, right? Like just including the non-linearity somehow. Like the layer norm on the definition of the RASP. The way they added the softmax. But okay. You could also probably like just consider it part of the MLP or something. That's already a part of a arbitrary function, but yeah.
Layer norm is normalization over the features, right? Like
Over the the activations, but yeah.
like for each token embedding, you subtract the
That
mean.
should be layer norm. What's the other one called? That's over batches. Batch norm, right? Yeah. Which is used in CNNs more, I think.
That seems weird. Right. But okay. Going to wanted to
This?
load it, but I'll do that later, I guess.
Like they don't. I'm aware it's part of the attention, the K and Q, but they don't explicitly say or define, I think. Kind of is. They define everything, but they don't define that.
Which one?
The queries and keys, they use the Q and K variables, but they don't say anywhere. Like they start using the variable and they don't define it. They don't
The
give it the
query and key
dimensions.
is the activation sign, as I understand.
Yes. Oh yeah.
So it's not. You don't need to define it because it comes from the previous layer.
You said previous layer.
Yeah, it's not it's the activations, not the
Yes.
it's of the model. So it's a variable. It's not the program. The program is the operator.
Hmm.
Right on the first layer, it's the comes from doing an operation on the. Actually, how do you get them? Does it say?
A is a matrix, and you use the fact that they don't. There are activation variables, and those are defined d times. Okay, dv.
Like they are parts of the. Okay, yeah, I know what they are. You are They are subdividing the token embedding of that position into a query and key variable parts, as I understand it. Right.
Yeah.
The dimensions is inside the parameters. Env is the layer of the input, right? Yeah.
Or like it can be any any variable really though that it's there.
So it's kind of inconsistent. They define absolutely everything, and then they don't define this. But yeah, that works.
No, but the thing is not defined because it's a variable and it can be anything that's on the embeddings.
Okay. Okay, I see. Okay, that might make sense, yes.
It's basically like any, variable of this size. So like, like in a general RASP program, it can be anything. Here in the transformer, it has to be on the input. So if you try to train into a one layer, it has to be the token embeddings.
I think I'm seeing it there now.
Right. Anyway, was it?
It's the yeah. You could say it's the cave or cave activation variable, or yeah. It's like kind of indexing. Okay.
Isolated the linear layer notation. Let me. It's for the transformer leading up to a represented by the variable. The input layer. Maybe here they give one example, so it's easier to see. Okay, for each attention head there is 4 selectors. You can see examples here of what the queries are. So for the first one, case the positional encoding and queries the tokens, and it has some. Okay, so it's the positional to the token to the token, and the positional to the positional, and the token to the positional. Okay, makes sense. You can see how all this is also you could put it all together as a thing from the positional plus the token to the positional plus the token, which is just the normal attention. And this is a way of decompositing it in multiple things.
Yeah, makes sense.
Alright. To output variables. So they aggregate the 4 things. The position on the token. Okay.
Hello, Rambert.
You're probably not going to like this paper because it's a lot of math.
We're deciphering the math, yes.
Yeah, I mean, so far, so mostly, okay, so what we're seeing so far, so this is, so the paper is trying to decompile models into RASP. RASP is just a fancy programming language with describing with a lot of math that has a bunch of operations, has some select operations, which is basically like doing the key and query part of an attention, like the pick a token.
I wonder how similar this is to tensor logic, which I haven't read yet.
Yeah, I heard about that.
Say again?
Oh, I heard about that in the MLST podcast.
Yeah.
His interview.
I don't know
Yes,
anything about that, but okay.
Seems to be also for a language, more general language in which you can describe most AI architectures, including both neural and symbolic, in one language. So, one mathy language,
I mean,
putting everything into tensors.
everything as like, I don't know, a lot of things. You can describe them
Yeah.
as Turing machines or as I don't know, Minecraft redstone circuits. So it's
Yeah.
kind of I don't think that maybe it has some nice properties.
I really wanna read that paper. Yeah, it seems to be like unified way to.
Okay, so
Yeah.
Okay.
they anyway. So I kind of not getting very excited today and not.
Yes, let's not get distracted.
8% residual stream. So they decompose the model in this thing. And they do all this. The question is, what do they do there? Because this is a nice thing, but this is only sound did basically nothing, right? The thing is the pruning, I think.
Yeah. Pruning is, I guess, important, and also their method, like if it can be automated or not.
Yeah, because
So-
so far what they did is they took the transformer and put it in a slightly different, fancier math way, and it's still like the same size, right? Like this is literally just the operation over the position. It is going to the operation here is going to be the actual weights anyway, right?
Yeah.
Like so far, I don't see much how it makes it more interpretable, but I'm.
No, I think
Yeah,
the idea is they do pruning after and try to do the kind of circuit search. And it could be the case, I don't know. It could be the case that doing this is like a better way to doing circuit analysis or something, where the kind of circuit ablation or something like the same way that maybe doing sparse encoders is better than doing it with neurons as the things you ablate, but I don't know. We'll see what they actually do.
And
Because
it's
I don't know how well I will do it from the parts we have seen.
so it's somehow easier to prune it when you translate it to this language than normal
I don't know. I
transformers.
think that's if it's useful, it's because that is that.
Okay, let's see.
It might not be. It might be bullshit and not very.
Yeah, let's see.
Already much. Okay, so it makes sense. So they have some primitives in the library, and they try to simplify the matrix to use decomposing a bunch of use of those primitives. Which that makes sense.
I like how the element-wise operation function is just written like a programming function like this. Inside all that math. Mathematicians never write it like this. Yeah, this is great though, I love it.
Need to replace symmetric. We remove for each aggregate operator, rotate to replace later inputs with 0. Okay, so they are trying to see which parts of the agreement operator actually matter, right? For example, on here, if you only care about the positional encoding, I think for something you might discard the part so it looks at the tokens, right?
With what criteria, like accuracy?
They say it here. Sorry, match accuracy. We measure match accuracy, the friendship of input instances where the program gives the same response as the original model. So yeah, like seeing how how much it changes the outputs. Within the compilator to be causally faithful if the match accuracy is more than 90%.
I see.
Okay. We translate removing inputs from the final software, replacing them with a constant absorbing to the bias. I'm not sure I completely understand that, but okay.
Oh, I see. Into the TV.
The causal punishment trigger because the size of the program guaranteed material is exponential in the original transformer size. Aha. Yeah, this is the thing. Wait, what was the theorem? 3 points.
Hey, Fars Forum.
Hey, sorry I'm late.
We're in the middle of deciphering the maths of this paper. At the end, we compute next to.
Yeah, so far we look at this and it so they do this slightly different version of the dialect of RASP, and it they have this fancy math spreading that it has a bunch of operations that like a select operation that does like kind of the same kind of thing as attention, which selects a thing based on a key and query, and some operation which basically some matrix, and it also has an arbitrary function to represent the MLPs, and with they show here how they decompose the transformer in a bunch of RASP operations, and we were looking now at how the because this is nice so far, but that doesn't actually help with interpretability or anything, because that's just basically the same model but in a slightly different notation, right? So the thing they want to do is do pruning to try to simplify this RASP thing into something simpler, that they have a library of simple RASP library of simple operations, and they try to somehow transform the super complicated thing that is just literally the model but in RASP with a really big operations that are basically just applied the weight matrix into some simpler thing. Yeah, I don't know how they do it well into that. The first thing is for each aggregate operator, which I think is just doing a sum, but not sure. And here, for example, they describe
some of the selects.
The attention as they do a bunch of selects from with the position as k position. It is the positional encoding and the token as query, and they they do all the combinations with token and positional and positional and token and positional, and they try putting zeros in different elements and see which ones don't change the outputs to see what actually matters.
Well, the aggregate is more complex. It has softmax in it.
Oh, so that is the aggregates adding
it's summing softmax of the alpha sums. Yeah, of the alpha operators.
Yeah, isn't it either softmax or clipping? Isn't that the two ways to approach it?
Either
it's
is
just that
explicitly
the one
defined.
operation has softmax because they're trying to do the same kind of thing as transformers.
Yeah. Clipping would just lose a bunch of signal, so.
Yeah.
But I guess their method only works with like one hot embedding. I don't know if it works in general.
Oh, it doesn't have to, right?
Really?
Well, not for what they're doing. No, it doesn't have to, because there's nothing mechanistic about this so far.
I mean,
like I'm wondering. Sorry, go ahead.
Oh no, I mean that like here the positional is one hot embedding and tokens are one hot embedding, but they could, since A is a matrix, but arbitrary matrix, it doesn't have to be one hot encoding, right?
Mm,
In fact, the output already doesn't have, like the input is on one hot encoding, but the output doesn't have to be a one hot encoding.
yeah, sure. Right, output.
Although I confuse why they do one hot encodings here, because how do you like here the positional embedding at the model is actually not a one hot encoding, it's some other thing. So
Yeah, exactly.
it seems like it's going to
Why do they not define it more generally? Doesn't the GPT-2 model include normal positional encoding?
yeah, and also the K makes like okay. I think you can do everything anyway. Like you can describe any operations you do with the like that the embedding has differences for different tokens as a bunch of bigger, operations for each thing. But that seems like a weird way of doing it, right?
Yeah, they're using a very strange abstraction here where they don't they're building essentially what looks like a map. But I honestly don't know why they're building it or what they're going to use it for. I think maybe this is just essentially building a translation matrix, like between RASP and the transformer architecture itself. I really think ultimately that's probably what this is. And this is just the assumptions that they made along the way and found a way to do it that probably contains a bunch of noise and garbage from the assumptions that they made. Which, by the way, is true of literally every single machine learning paper that I've found thus far. It's full of assumptions, renamed terms, and a whole bunch of noise that they try to jack up the signal to get through the noise instead of simplifying their approach. So if you're asking why are there no general solutions, it's because this is a paper written by machine learning engineers, not by scientists.
Anyway, so what I was saying. So
arbitrary tensors for selectors and X token projections.
here the can be recovered as.
I think this was written by mathematicians that are heavily Python built, actually.
E token. Wait. E token. Well, E is the token, but okay. So they are doing the embeddings here. Oh, okay. So we are wrong. They are using the embeddings. They are just putting them that's all. Actually, no, I wasn't getting right. They are putting the embeddings on the as the part of the operation.
I see here, yeah.
So
are
like
the embeddings, right?
on the first layer, the operation is turn this one hot encoding into the token embeddings, and then do the K and query part, right?
Okay. Yeah.
Token embedding matrix, I see, yeah.
So
extracted from GPT-2. Okay.
So okay, going back to the learning part. Okay, so the aggregate operator, I understand the aggregate operation is just adding the numbers and then doing a softmax. Or adding vectors, I mean.
Say again?
So the aggregate operator is just adding the vectors and then doing a softmax, right?
Yes.
Softmax and then weighted sum.
Okay.
Yes.
It's weighted sum.
You first compute the ij's, ij's, where you sum all the alphas and do softmax, and then you do the weighted sum with the vj.
What's the last thing here on this aggregate? So this thing, what's the last input of the operator?
That's what you sum with in the weighted way.
Okay.
You take the aij's and multiply with the vj's and sum all of that for all ij's where j is smaller or equal to I. Okay.
Okay. So comparison methods. Okay, going back to the comparison thing. So this comparison. Okay. So the transform the programmers. Yeah.
Like that's the causal autoregressive attention. That's causal masking. The j is smaller or equal to I think.
Okay.
Position I can only look at the positions up to and including itself.
Also, we try to remove inputs for the final softmax, replacing them with the constant substituting the bias. Where is the bias on this thing, actually? The RASP operations. Do they put it? I mean, you could put it onto aggregate, part of the aggregate or something, but.
Isn't bias? Isn't that when you put to select just one v is the activation variable and one operation? Wait, I'm not sure if that's correct.
Oh, they have an example of figure 9. We can do that, but yeah, this is like the causal pruning is similar to causal aberration stuff in interpretability.
Mm-hmm. No, I was wrong. What I just said before.
Removing edges on the computation graph makes sense. Isn't the causal pruning is trivial? No. So theorem. This Attila's problem defining the same input argument. It can be specified time for the transforms parameter. Due to the pseudo stream at each layer can be recovered linearly from set of variables. Huh. I'm not completely sure I understand. So here they talk about because the size of the program guaranteed by theorem is exponential in the original transformer size. I don't understand that, right? Because
what exactly you don't understand?
like, what they mean by size of program here?
What exactly? Size of. I would say that's like the number of like symbols you need to.
The caution about the causal pruning is not trivial because the size of the program is guaranteed by the theorem 3.2. It's exponential in the original transformer size. But right, yeah, here unfolding the full program, like you already have a program that is just the one single like this is already a program, right?
Yeah, it should be all the things in RASP should be programs that are
No, but I
composed
mean,
in
there
various
is
ways.
only 4 selects. What is this? Like, is this the number of selects? Like, what is this thing with exponentially more selects or exponentially more whatever? That they are, how they are decomposing it. Like, they think they can give you an example here, but I think they are not decomposing it this way. Maybe we need to look at appendix, like the one that explained that. I don't know if you know what I mean.
Transformer size, so I guess I would. Yeah, I'm not sure that's correct. What I'm thinking now, since it's related like exponential in the transformer original transformer size. Do they mean like
I can imagine
parameters?
things like, okay, so you turn the transformer, you get an exponentially bigger one. If you, for example, turn a transformer into a addition tree, so you could do a thing like that where you are doing, maybe they are decomposing that way, where you are doing for each tiny thing all possible. I'm still not sure what the full decomposition is here, but okay, I'll keep reading. Maybe it's playing before and a bit more after this, and otherwise I'll look at the appendix. Okay. Well, it will consist of dedicated dimensions between the prune model and the original model, along with sparsity penalty. Aha. Space. Meanwhile, we also train this function, land or, well, yeah, for each layer not to reverse the KL. No, someone left. Oh, they wrote something on chat. Oh, Sagi left. So because I feel Sagi was kind of also following the paper and was saying interesting things.
May rejoin.
Anyway.
Yeah.
We then replace the layer norms and the model. It's kind of hard to read, harder to read paper than I expected, but yeah.
Yeah, same. I'm also still slightly sick, so I'm slower than usual as well.
Here today. The motivation for this motivations, okay. I mean, I think the idea doesn't seem that complicated. Any person fees priced by element-wise operation. Oh wait, what is this? Oh, element-wise operations are the like, okay, I can see why it will exponential, it will be exponential. Maybe that's why it's exponential on this list of simpler operators. Okay, so
most frequent program is aggregate project softmax.
Tony, do you understand this? Okay, so we try to explain every element-wise operation by replacing one's product. What is element-wise operation here? Because on the
That's defined on top.
yeah, but here can use arbitrary detections.
Go more on top.
It is mentioned.
More on top. Element-wise operate. You see defined v equals. They just define it there. At the bottom. They capture MLPs.
Okay. The element of separation is just the arbitrary, the MLP part where it does. Okay, well, I understand. Okay, that's that thing. So they did explain it by replacing them with non-primitives. Okay, and the other part was on the. Okay, so on the aggregation, they try to find which parts matter. I'm still not clear how they divide it, because if they divide it like this, it's basically just getting them to figure out if some attention head is cares like first for your circuit specifically which attention heads matter. So you are basically dividing into attention heads, or you're doing the same kind of causal ablation as if with the previous literature where the people ablated attention heads. I think this is not ideal. It would be better if you were able to do something more clarinal, but okay. Maybe not. They are not doing that because there are some things that tell me they might be doing something else, but we'll see later. And on the so the aggregate, they are trying to ablate that. And on the element-wide operator, what they are doing is trying to find one of the primitives they handcrafted and see if they matches what the MLP is doing.
Oh.
Where position?
Oh, in the second project, special operation uniform selection. Q equals K uniform selection. Okay. I'm now gonna look at the example more. So they define these programs that map to various parts of the transformer, and they just ablate it from the transformer, the corresponding programs, and see if it matches.
Yes.
Still. I guess that works, but like, why do you need...
Okay, for the aggregate thing, if I understanding correctly how it works, it seems not exactly because they separate the positional encoding and the tokens for some reason, but unless they do a more granular aggregation, it seems to me that it's equivalent to do pruning on the attention heads. Right?
Correct.
Mm-hmm.
And the it's a bit more than that because you can prune only the attention heads carrying out the positional encodings. I think there is something weird about that, but I'll talk about later if I'm not sure. With wise operations. Spreading process transformations. Okay, so but on the MLP they are doing something else, and the MLP they are trying to the element-wise operations, which in the RASP program are the equivalent how they are encoding the MLP. They are trying to replace the MLPs for this basic library of operations that they basically made up by hand based on things like unknown things like induction heads and all that, and they are trying to see if replacing it gets high accuracy. I guess you could see this as like there's some toy model interpretability that you could see as this automating in that people are also kind of looking at the things and see if it matches something like that. But I feel like in practice, when you are doing actual token, toy model interpretability, you are looking at the thing and trying to come up with what simple operation it matches instead of always using known ones. But yeah.
I feel like you could define the circuits in a simpler way than this.
I do not understand all of this part, but yeah.
They like abstract away transformer and certain.
On the input side, we store the interpretable activation variables that are fed on the element wise open. On the output side, transformation feeds into embedding. We can linear transform it to have it output dimension.
No, it's a mirroring, it's not abstracting.
I mean, it's just like the original RASP thing is just equivalent to a transformer. Well, it's equivalent to a transformer without the layer norm. Did they just train the transformer to not use the layer norm? Or like not use the layer normal linearity, which is kind of weird, but I guess maybe it works. I don't get why they couldn't add a layer norm operator to RASP, but okay.
Oh, interesting. I'm just noticing, like...
My real quick, my read was that most of those anomalies in this paper, while I don't fully understand the specifics of all of it, seem to either be due to an upstream assumption that they made or attempting to mitigate a consequence of a previous decision on the decision tree, which is how a lot of these papers go. They make an assumption or they inherit some kind of logic chain, and then that just cascades down the rest of the paper. So this is very clearly just like the only way that they saw to make RASP cooperate. They missed a whole bunch of general ways to do it, in my opinion, and you're just describing one of them.
Seems like a language that's kinda equivalent, so it may be easier to reason in it.
Why is the method supposed to have the okay. So why was exploring why some okay, so yeah, so they do this. There is oh wait. I saw something interesting here. If no primitive at serious enough might be interpreted by expecting its inputs and outputs follows. On the input side, we store interpretation of activation variables that are fed. The operation fits the embedding. They have. Maybe remember this is slightly interesting on this. This technique can be reading as a principal adaptation of logic lengths.
Oh.
Could I see this? Let me see this.
So they are when they don't, they try to replace the MLP by some specific functions, and when they don't, they somehow use logit lengths or like a RASP version of logit lengths.
Yeah, there's multiple logitlen variations though. They didn't explain the variation.
No, it says so they did explain it. It's just kind of explaining a very mathy way here. So they start interpretable activation variables for different to them. Okay, yeah, they have this is the activation variables that they have on the output. Linearly transforming to have the output dimension. This is just the this was just the what was that? Okay. For encoding token information. Okay, so it's just into the tokens. I'm not sure how they giving a different activation variable as input. Okay, so I understand what they do. They do the logit lengths on the component, and they try seeing how different inputs change the logit length result. I don't know if that makes sense.
Oh, I see.
Like they have some they have some model where they interpret the model up to some layer, and they have some variables that they think the model is doing some, like for example they have some variable that is like the position of the model, or the position of some token in the sequence or whatever, and they know the previous layer somehow is calculating that, but doesn't know what the next layer does with it, because it doesn't match any of the next MLP specifically doesn't match any of their primitive functions. So what they do in this case is basically do logit lens and try to see what happens. But that sounds like they have to do it manually. Yeah, they do it manually, basically. They're just describing in a fancy way. They look at the logit lens and see how changing the inputs changes their logit lens result. So I don't think people do much. I guess it's hard, like normally, there's not that many people actually reverse engineer doing models. But yeah. Displaying A/B tensors. Select and project. Okay, yeah, how they do the attention part, or the select part? We replace them with a matrix from the library. Okay, so this well, it's not possible with the mathematics to sparse and have integer values. I don't know how they do that, but okay. So this is just they have some attention matrix, and so they do the same kind of thing for attention that with MLP. They do this optimize the matrix to be sparse and have integer values. That I don't know. I guess it's just a fancy way of the thing I normally do, which is you look at it and see what the numbers are. See what the plot at them and look at the things that look bigger. But you could, I guess, sparsity. You could do a thing with sparsity that makes it easier. You might miss things that way, though. But I guess if you do it in a way where you are matching the 90% of the more than 90% accuracy, it should work. Okay. So what is this paper? A formal framework for this. Okay, so this is the length framework. We build a problem sequence predictions. Implement by feeding the logit syntax to no inherent probability of sure this simple statistics with the models. Okay, so they just logit syntax to variability level for each symbol. Okay, they just put the thing as correct or not correct. I feel like formal was called no internet properties. I guess that makes sense. Doesn't matter that much. Like I don't toy problems where I just put the normal thing where it outputs a probability and don't do this weird step. But okay, I think it does some sense in doing it. Performance setup of Huang et al. Iterate the models. So they tested this length generalization thing. So they tried different length communications, and they try to decompile it. When does the compilation succeed? I'm curious how much they also they had to do the manual part versus their simple functions matches. I guess you do that manually more times, you get more functions that you could put in the
8
library.
showed languageization and 3 didn't. Interesting.
I mean,
I'm now going through the unique copy example.
okay, so they select. Okay, so first it's query k, and the operation is k equals q minus 1. Makes sense. So the position is, this just look at the previous position. Okay, so now I understand if the attention is actually not that hard to read. Aggregate token. I think we have already spent some time reading the original RASP paper and understood the operations already. We will have this will have been easy. It will be like just so this is the same but with a softmax here or whatever, and yeah. But select Q token operation. The token is the same as A1, where A1 is the aggregation of S1, and S1 is the position on each token. Okay. So you take the previous token position. Yeah. So this will return a 1 on the, yeah, and then you add them on the token. Right. Yeah, I feel like this paper is maybe not the best kind of paper for the reading group because it requires a lot of spending time reading details of this, but understand. By the way, Relbert, do you want to next week do the maybe explain the logit lens stuff?
Like which variation of logit lens? I mostly did logit lens and Cody models, and I made.
I mean the logit lens in Cody models paper from Neil. And did you say there were two papers?
No, they didn't. No, it was a last strong post, but I built on top of it. It was only like a small exploration.
Yeah, but
like
I think,
they didn't do stuff like look at tuned logit lens, which I did with my own experiments.
yeah, we can read the. I haven't read that, so we can read the Cody thing. Like, I think you
Sure, I
mentioned.
guess I could show how the code works, but like.
Yeah.
The most I did for that is like making paper, like you could see like I made a less strong post on like looking at like other variations and fixing
Yeah,
the
but I was more thinking of looking at the original.
Yeah, I know. Yeah, looking at the original. Yeah, if you look at the original.
I mean, you can mention something about theirs, but mostly for you to explain it since you already know about it.
Well, I don't think I understand it the best, but sure.
We can look at it together, but yeah, okay, we'll just. In any case, I think I'll pick that for the less from post or something. But so you mentioned there was a less from Neil had a less from post, and but there was something else. I remember you said something about there were two things which we could look at. Apart from Neil.
Yeah. So the less strong post from Neil is, can we interpret latent reasoning with current interp tools? And the most, like, it's a very short thing. I don't think it's a full reading group. So I feel like the main thing we could focus on is after we read that, we could look at the Scratchpads paper, which the Neil paper refers to.
Okay. So can you link both on the reading group channel so I can put them for next week?
this one. That's the Neil one. This is the Scratchpad one. And then I did my own thing on top of this, where I made my own version of thought anchors that works on Kodi, but that's not something. It's still incomplete. But I was able to
so we
complete
can
analysis.
look at both next week.
Those two I recommend. The Scratchpad's going to be the main paper, but the Neil one would be like something for like an introduction to how like
Okay.
since they did similar methodology but like different ways to look at the Kodi models.
Real quick, I would really love to hear about your work in the context of that paper next week, if it's not too much.
Sure, but like that was like this. Yeah, I could share. Yeah, here's the less strong post I made. I made this in like a weekend, so like kind of progress. But like I still like.
Dude, I'm not gonna judge you. I'm just interested. It's okay.
Oh yeah, here. That's what I did. I looked at so basically what I was able to do was I was able to like look at like Toon Logic Lens. I was able to show like Toon Logic Lens like was able to show that the model for latent reasoning had the answers inside the computation.
Mm-hmm. That's
this
funny.
did
I found
not
the same thing in my grokking research.
Yeah, but like the initial Neil, if you look at the initial Neil last rank post, let me just screen share that. So yeah, the initial Neil last rank post, they only use normal logic lens. I do not understand why they only looked at normal logic lens, and they only showed the intermediate steps are shown inside the model computation. I was able to show that with like Toon Logic Lens with like different variations of Toon Logic Lens. You're able to actually show that computations inside the model itself.
Oh, dude!
So
That's
I showed the
fucking pattern and a half.
So I showed the Kodi models actually store the computations inside the odd latents for the answer. So final answer mission is during the middle layers for the odd latents. And also looked at the for my less rank post, I looked at the entropy. I looked at the entropy and showed that the entropy for the odd ones were the highest. And for if you look at the top K outside the top one, it turns out the even ones actually contain final answer emission the most. So Logic Lens does not pick this up, but if you look at the intermediate answer detection, the even ones actually store the information more, which matches the Scratchpad paper. So yeah, most of my results kind of confirm the Neil post and the Scratchpad post, but show you could also like
okay. That's super
I'm currently
cool.
building a Thought Anchors extension to try making Thought Anchors that works on the even or odd latents. My current hypothesis is because the odd latents or even latents both. So the 3 and 5 latents, 3 and 5, are the highest like change in accuracy in the Neil post if you replace the activations for those specific vectors, latents. So and then they also have the highest entropy values. That's my unique finding I found. So my current hypothesis is if you like make a thought anchors and you like resample only latents 3 and 5, you're able to probably like show that the model like has different routes to thinking of a problem. So my main reasonings for why I think the latent reasoning models have the highest increase in accuracy after latents 5 is because latent 5 is the latent in the Kodi models that has the highest entropy across like these math problems. And also like the fact that they store the final answer. Those are my unique findings on top, but that confirmed so like the Neil post found I was just exploring like why the things in the Neil post were happening. So over here in the Neil post, they talk about how they look at how like the final answer mission for steps 1 and 2 were the highest at latents 2 and 4. I found something similar for my post, but I looked at latent by latent, layer by layer. So I looked at the layer by layer to show like look at it also. Not sure why they didn't look at that. And then over here, they show how like latents 3 and 5 are like had the highest like performed like the highest for like the effect on the performance. Like increase in accuracy on the 5th layer. This kind of matches here. Results here. The entropy for layers 5 is like pretty high, so it kind of makes sense. And also if you look over here in layer 5, if you only train it on layers 3 and 5, interesting Kodi model for Toon Logic Lens, it doesn't show final answer emission. You need layers 1 to be included. So you have to like include 1, 3 or 1, 5 works, but 3 and 5 does not work.
Yeah, I
for
mean,
training
you can't
purposes.
fall into a basin if you don't have the first fucking layer. That makes sense.
Yeah, but like you only need the 3 or 5.
Yeah.
To show to have the logic lens show the final answers.
Yeah, that makes sense.
Yeah, and then over here, I'm just looking at the Neil post like right now, just like taking like showing like so they looked at like third and fifth had the notably decreased accuracy. It matches my results here, where I found the 3 and 5 had the highest entropy outside of layers 1, latent 1, which I feel like is pretty obvious because it's the first latent where you're converting the normal activations into latent reasoning activations. Yeah. That is the TLDR what I did. I honestly don't think it's that impressive. It was like something I just saw the last strong post and I just built on top of it because I was like, oh, these are like interesting things I see in the last strong post. Might as well try explaining them.
I mean, that's exactly what brought me to self-modeling and then eventually to grokking. So
starting to understand the example.
You did the grokking paper?
More.
You looked at the grokking paper? Oh, nice.
Oh yeah.
What do you find?
Well, in order to do my research at all, I had to reproduce it and make sure that the things that I was doing.
Yeah. But like, what do you do as an extension on the grokking paper?
Well, during the grokking paper, I went ahead and tried a bunch of oddities. For example, I was playing around with severe overparameterization and seeing how that affects grokking.
Yeah.
I found some very interesting results around 22x and 88x overparameterization for Fourier models, which was very interesting because I was like, okay, except for like obviously scale matters, but we don't fucking understand why, right? Like it's a giant black hole in the knowledge of machine learning.
Yeah.
And I just got to tell you, how little we know about how these hyperparameters interact with themselves and each other bothers the shit out of me.
Yeah.
They are spending literally trillions of dollars and they don't even know the rules of the game. So I figured, well, if grokking is the transition, is essentially the creation of memorizations, right? Which are essentially information that the model needs to remember, and that's how they store information, either as a shard of information or as an algorithm that uses information either from the context or stored in the model. This also kind of suggests why models or how models contain information. However, they can be wrong about things because that representation can get damaged by, catastrophic forgetting or a different kind of weight decay, fucking up something it's not supposed to, or literally millions of different things that can affect the parameterization or the geometry of the space that the model is attempting to exist in. So I was saying, okay, obviously grokking is being affected by this overparameterization, and it is also affecting which solution that it finds. If I constrain the parameterization quite a bit, then I'll only get a generalized solution that maybe scores like 0.74 ultimately. Like it has most of the Fourier transforms, but it's a generalized solution that isn't actually that effective. If I give it more parameterization, more dimensions to essentially move through, or more dimensions that move through it, I guess is the better way to talk about it, then it essentially can find the missing generalization pieces and then get a full score on all 41 of the actual Fourier algorithms. So I was trying to figure out, first of all, why does that matter, right? And second of all, what other hyperparameters matter? So I went ahead and I essentially said I essentially said that when something crystallizes, which is an annealing analogy at this point, when something crystallizes into a memory, in what order do the components of the model from Q to MLP, what order do they crystallize in? And when is the entire thing set in the model crystallized as memorized, or is actively contributing to computation as a circuit, as a generalized function?
Yes.
So I was able to distinguish those two different things in my research, and then I was able to essentially, with with
still in
pretty good
progress. I assume it's still in progress, right?
Oh, dude, as you know, grokking is insanely massive. So, of course, it's still in progress. But I have literally hundreds of certainties based upon about 3,000 different experiments and data points.
Nice.
So I'm already pretty far in, and I've already figured out some things that I'm actually very certain of and some things that I'm not certain of. The thing that I'm most certain of and that actually is most consequential is the fact that I can say with certainty that the components crystallize into memorized solutions and then grok into generalized solutions at different times, regardless of the task.
So, like, certain parts are... So, like, could you give me an example of this?
Yeah, I could give you an example. Sure. An example would be that... Okay. You're on the edge of my actual machine learning knowledge here. I'm going to attempt to explain this. You may need to correct exactly my implementation. Okay. The first thing that gets crystallized, essentially memorized by the model, is the attention routing, right? Because routing essentially tells you where you need to go in the model to do the thing. Sure?
Yeah, I see this. I buy this.
Loosely, right? Unfortunately, all I have is generalizations. I'm a sysadmin by trade. Machine learning is a hobby. So that is the first thing that essentially gets memorized as to where everything is for this particular task, right? As it goes further down and gets all the way down to the MLP, when the MLP essentially stops changing the circuit itself, it is considered fully crystallized. And at that point, you have either a fully memorized solution. A good example would be a linear lookup table for the Fourier transform. That is a fully memorized solution that model is the shape of a linear lookup table. And when you run the gradient, it literally does linear lookup mathematics and then gives you the answer at the end out of the LM head.
I see. So, like, the most extreme version of learning is basically just like the equivalent of like a dictionary where you put the key and value to get the value, I guess.
Well, yeah, and so that would be a successful memorized solution. But as we know, it is not even close to as efficient as the Fourier generalization, which literally is why we can decode radio waves now. Otherwise, if you were we were doing linear lookup table at first when we first were trying to do Fourier transforms, and that's why they needed, a binder of mathematics just to resolve one signal. Then we discovered the algorithm that generalizes all 41 of them, and then suddenly we can do that with a crystal.
I see. Are you looking at all grokking papers, or were you looking at like the Neil Nanda grokking paper?
So this has all been based on just on the stuff in A power.
A power?
Hang on, let me find the paper. It's by A power, which I do not fucking understand what the fuck that means. There's actually like 4 or 5 authors.
I haven't looked at grokking at all, so.
Grokking is extremely important. It literally is what dictates what kind of network is in your model, like what kind of model is actually in your hyperparameter space.
I see. Could you send it through DM so I could probably remember it, because I'm probably going to look at them later, not just glance at it.
Yeah,
Those are pretty interesting.
Trying to grab that now. And anyway, the crystallization order is what I was talking about. It's actually the most consequential because I did that across language, arithmetic, modular arithmetic, and a bunch of mixed tasks. And the crystallization order for the components is exactly the same for each one. Grokking works exactly the same regardless of task.
Oh, I see. That's nice. I feel like it's a great paper if you actually do it.
I will. I just need more evidence, which I am well, actually, I need to interpret the existing evidence that I have and get more evidence.
Yeah. I honestly don't bother to make papers yet because I'm just doing less strong posts because it's like easier to publish that and like give out to the world.
Doing what posts?
Less strong posts.
I'm not familiar with that. Maybe I should start posting my stuff there.
I don't think people actually look too much, but like you could somebody's probably gonna at least a few people probably look at it. Depends.
I would be amazed if the big labs aren't straight up feeding those right into a model for ingestion and flagging ones that
yeah, that's probably fair. Yeah, so I guess you're gonna probably try submitting it to a conference, or are you gonna put it on Cortex only?
Interesting.
Well,
this sounds like a conference
sure yet.
If you actually could get this all done.
I mean, I'd be honest with you, man, I know jack shit about academia. My first thought to do it with is to just like fucking build systems based off of it because that's what I do. But like for example,
so there's induction head in the special
Half my time is
in
just
the
spent
unique
on
copy
college.
circuit.
It's not even
Okay.
spent on research.
Yes, they have induction head. Going back to the paper, where to go? Yeah, so yes, they have induction heads on the library. So I think their methods automatically detects when something's an induction heads. And
I think the line 3 is yeah, line 3 is the induction head in the unique copy.
Where are you on the? Are you still looking at the
unique copy example? Yeah.
Okay, line 3 induction head. So you're saying the line 3 is induction head. Okay, so induction head. Yeah, I do know. Yeah, the induction heads are usually made with previous copy head, and which is here they have the previous position, and then they have the I think
Yeah, like
that
when you are at token 1, you go. Wait, how is it visualized? Position 7 is 1, 2, 3, 4, 5, 6, 7 is free. And that's what you want. When you're at position 7, which is at token 1, then you attend to 3, which is right after 1 in this case.
Wait, but don't you? So what you actually want is for. All right, you want to the next one. So you want to get the
At
previous
which
one. Yeah, okay, that makes sense. You want the induction head because you are trying to copy the list, and the transformer output is shifted one, so you want on each one output the next one. But yeah, you just make an induction head with a previous head, previous token copying, and you, which is S1, right? But it's like, you know, S1, and then you do S1 and you get A1 by aggregating it, and then you do the S2 where you take the token and you take
the A1,
and A1 is just the aggregation of S1.
yes.
So you are just, so it's if K equals Q, so if the A1 equals the token, yeah, and K, and you do a special operation if K equals the beginning of sequence. Okay.
I have to write. I keep coming back to all the definitions. Jesus Christ.
Yeah.
I
So
just
when
need
you
to
do the
take this
select,
whole.
what
Yeah,
is
I know what.
the output exactly? Is it?
I think I know. Yeah. Or
So here, if since this K equals Q, is it on, is a list of, you take a matrix and you have ones, like it's a token by, so the select operation has as output the what was it? Also, I feel like Firestorm and Trevor were talking about Firestorm's thing, and like we kind of interrupted going back to the paper. Maybe if you want, you can, and you are not as interested on this thing, you could go to a different, keep talking on a different channel, maybe.
Or after this paper.
Because I do feel like at this point, maybe only me and Burnie are interested in reading this paper, so I don't know.
But it's okay, now I'm starting to think this paper is interesting, because that's technically an equation for induction heads. Which is amazing.
Where did they say that equation for induction heads were?
Induction heads are pretty. What did you just say?
Oh, like they think they found this, like, shows you could find induction heads from the paper.
Yeah, like at the end they say when you look at the unique copy example, at the end you say the program recapitulates the induction head motif.
Yes.
Oh, if it actually works, like, that's great.
So it's how, I mean, it's not that like it's very hard. It's that hard to doing another kind of way of doing programs. So of looking at it, but yeah, you basically just find induction heads by seeing if you can. They have a like a induction head operation matrix, and they see if you can replace the. If you can replace the.
Yeah, oh, they're replacing it at the function level. That's what you're trying to say. It's not no, it's not a precise definition. It's not a derivation at all. It's an approximation.
No, they are replacing it and checking that it gets the same output. So it's a way of detecting.
Yeah, but not how. Not the same way that the transformer network does it, though. Again, just like every other ML mistake.
It is like, it's same in the sense of that you hard code exact like one like big numbers, but it's not the same in the sense that transformer weights are more messy. So it's kind of approximating the transformer weights that are actually learned by removing the noise. That's not accounting for the noise.
Yeah.
In the
and I will actually point out that
parts matter. I simplify the networking away.
Yeah, like if you would ablate this, then you would destroy the whole induction head mechanism, basically.
Yeah, it's an approximation, a good one, maybe. You know, it also could be the best worst approximation.
Technical approximation of what transformer actually learns. I'm not sure if approximation is the good word, because it's more like what would be the ideal if transformer wouldn't have noise and the task was to
not
learn.
necessarily, right? Because it doesn't have to be that, because you are looking at a task, right? And if you are looking at a model that is doing something else, maybe the noise is just actually some other mechanism for a different task.
Yeah.
And you're just saying that the network is approximately working as a tension head, like it's an abstraction. It's just you're saying the network works as a tension head on that head for this task that you are looking at, that the model has the same outputs and inputs.
You could also describe it as saying it's an approximation because it cannot actually predict any perturbation in the network that is due to noise or harmonics of the noise with the actual task or with the model itself. It essentially cuts out all of that information just to be able to translate between the two, because the interaction surface between all of those is so complicated that the resolution of your data would need to be so incredibly high and your generalization would need to be so perfect that it would be nearly impossible.
It is not accounting for the other mechanisms if it's a more general model. Yeah,
it can't. And well, so that's the thing. If you either pay that tax for that data resolution and also in a highly refined general model that applies to literally all edge cases, or you hand wave it and abstract the parts of the signal that simply are too complicated. It sounds like they did the latter, which there's no other thing to do, really.
Yeah. Like, yeah, it would be nice if we could decompile also the noise in general and so on. Well, not noise, other
You know
tasks.
what? I would say a fun experiment would be to actually separate out the noise and train a separate model on that, and then have them attempt to predict each other. And that actually might work because it does get task gradient information from the noise. It's just not as much. Yeah, that would be
I think
interesting.
depends how entangled the mechanisms are as well.
Yeah, that's the thing. Just my experiments this morning showed that if the task information doesn't actually reach the network, then obviously nothing fucking happens.
Huh. Okay, I'm gonna now look much more into the induction head example. I think that's super interesting. I'll go.
Yeah,
again
I
through
actually
the
want to know what
definitions.
resolution of data they're actually doing here. What are they ripping out? What are they hand waving? It doesn't sound like a lot.
I think they are just extracting weights from GPT-2 and running for unique copy task and sort and other tasks. I'm not sure if they use some other weights. I think just GPT-2 directly.
No, they don't train GPT-2. They train GPT-2 like models. So it's like the GPT-2 architecture, but they are trained only on a single toy task.
Oh, for the record, that's what I do too. GPT-2 type architecture, but algorithmic and modular arithmetic. That's the standard.
Okay.
Yeah.
So it's okay. So it's trained only on unique copy, only on sort. Right, it was written there. 1 layer, 4 heads, I think, or something. Oh yeah, you're right. Yeah.
Yeah, sorry. That format is actually also used in Nanda's paper.
Yes,
Progress measures for grokking. Yeah. So that's actually why I picked it for my experiments, because that's the standard and it works great.
Yes. Yeah, I also like that
I don't think
paper
necessarily
because of that
Neil
reason.
Nanda what it is. It's necessarily the standard, but yeah.
Well, I'm sorry, the standard, the currently established standard.
For grokking, it's probably the best paper.
I guess you should also include the Neil mentees as well then.
As soon as I know what that is, I will. Thank you.
No. I mean like the papers made by Neil's mentees for the Neil mats.
Let me write that down.
Yes. Okay, let's check the unique copy example more.
Or I probably only look at the research phase Neil mentees though.
We won't. Yes. That's so cool, actually. How it's a relatively general way to express induction heads. But like, I feel like there could be some simpler language for these circuits instead of this RASP language somehow. Like, actually, maybe this.
I mean, the RASP language is not that complicated. It's just hard to. It's just explaining a way that's kind of hard to understand, but it's very simple operator, right?
Yeah, it is.
It's almost like you're just rewriting the operations in the transformer.
Yeah, like I think you could just take all these conditions that make induction heads, for instance, and write it generally just in the transformer language without going into the RASP territory somehow. Maybe not.
I mean, will it be that different? So you could do a different notation, but like if you are doing, like, you want to describe attention heads, I feel like the resulting thing is going to be similar to the select thing, right? It's going to be some matrix that you apply to some input.
Yeah.
To some K and query. You could also do them together, but this is a nice way of separating it. So I confused, but I didn't understand this.
So you looked through like the causal ablations and so on that they did later?
Oh, so the causal ablations? Oh no, I haven't. I mean,
I
the
wonder if,
cancel
like,
operation is
they-
how they find
Oh,
this,
yeah.
right? So they. I understand that to get this kind of thing, what they do is take automatically take a bunch of operations like this, like the k equals q minus 1, all that, like the induction head and all that, and they try replacing the MLP for that by that and see if it, and the attention by that, and see if it matches.
Mm-hmm. Oh yeah, if it matches, right? I see.
Like if the output and input of that layer match.
Yeah, that was the fraction of same inputs thing.
Yeah. They also do it on the level of the aggregation, which, as I understand it, that's basically if you the aggregations are there's a bunch of aggregations, but you can in the aggregations you see which parts actually matter. Like you put zeros on some of the components and see which ones actually matters.
Yes. This is cool, actually.
I don't know how much this feels like anything I will actually try to do it myself and see how good it is. I feel like maybe you can do some cool automation along these lines that you could also maybe have done without the RASP thing, using a different formalization of the attention heads to through a tries instance. You have a library of simple attention patterns and you try to match it to, like, I can imagine a programmer that doesn't do any of this math stuff, that just thinks of it as some in more like some more AI terms, in terms of a library of attention patterns or something, and you can try replacing it and do the same kind of ablation. I feel like this is still missing. This is worse on this kind of tiny programs for similar reasons to why it's easier to do interpretability on them, and this might not scale to bigger models without some notion of features, right?
Oh yeah.
Because this
Like
is still at the doing like the same kind of thing people are doing manually on transformers, which is doing like token level or attention head level interpretability, right? But they are not. It will be hard to represent on this ledger without something like a sparse encoder. Doing operations on subcomponents of the embeddings or whatever, right?
Yeah. You get the entanglement that you need to solve.
It works on these tasks, for example, because on these tasks the thing is doing is copying the entire model, so the entire token, but it will be hard to disentangle if you wanted to do something like copy the information about whether this token is a number or a letter, right? You could represent it with a RASP program, but it gets.
You would have to have maybe like some primitives for like number is this direction in the activation space, for instance.
Yes,
like the
but
features
it feels
essentially.
like for do that you need something like sparse encoders already, right?
Yeah.
Unless you want to do pruning on all possible directions, with all,
Yeah.
Like you could decompose it as the program as a infinite number of all possible way of doing, that for each neuron or something, select, right? But it wouldn't. And that's why the select. This is true. I think this is why here the select is Right. They're talking about the positional encoding, and the positional encoding is a one-hot vector. But on the thing where they talk about decomposing the transformer, they add the thing, the embeddings on the first operation. Here they skip it because it's not part of the thing, but that doesn't work. To be at the same time, on this paper specifically, they are not trying that, right? They are not trying to look into real models. They are trying to understand something about the generalization on this hypothesis they have about length, whatever, right?
Mhm.
And
Generalization.
so they just want a nice way of taking this kind of toy task and interpreting it. And maybe the fact that there is something into the fact that this kind of simple thing works in some cases but not in others and seems related to the length generalization thing. Maybe there is something with that, but I don't know how much to read into that.
Yes.
That part seems like the most sus and less, the more they have this idea on their heads and they're trying to explain it, but doesn't necessarily generalize. But like, it's not necessarily true, actually. I mean,
like, what makes I like even like if you try to find all the features, you still like you always, at least with CREM methods, you get the reconstruction error and so on. So like even if you somehow for every possible prompt that you put into some general spouse or atomic models, like I believe there is always some prompt that somehow you will have extreme reconstruction error or something like that, which you just haven't covered. Would be interesting to map the space of all possible features, but it also is different model by model and so on. So, oh god, complexity.
Yeah, the geometry of the space versus and where the model is in training all dictates that.
Yeah, entering data and so on.
Like if we had a map for how the hyperparameters actually interact with each other, we'd be able to dictate which solution that we want and expect how many training steps it'll take to get there.
Yeah, there's a lot of disconnected theory everywhere about hyperparams.
Well, you only need one. They interact with themselves, which means they interact with each other. If they interact with themselves, they probably interact with all of each other.
Yeah, I would say they are like warm up for. Yeah, I just noticed some paper that was talking about how warm up is like doing some magic at the beginning to like make the lost landscape more flat or something.
oh, they have frequently answered questions, by the way.
So that is actually a really, really good direction, but they're doing it the wrong way. You warm up is absolutely fantastic for certain things. You can use it. So if you warm up, and then you, for example, while the attention heads are frozen, and pass the signal from the attention heads straight through to the MLPs, without allowing anything but the MLPs to change, you actually will reduce the seed variance dramatically, depending on how much compute that you allow it to do that. This can actually be described as analogous to dreaming. When biological machines dream, their attention head is disabled, but their lower representational networks are, combining information. And when you have specific dreams, your attention head is actually being simulated, and it's even simulating other humans in your attention space. Like, what if my husband was my mother?
That's what you meant when you told me this yesterday or 2 days ago. I see now. Okay.
Yeah. So grokking
interesting analogy.
Yeah, well, it's an analogy. However, you can make predictions from this framework, and I do actually have evidence for REM and NREM and what they do in models. And one of the main things that REM does actually is it reduces the shock when you do stop the warm up and allow the because the MLP has been learning without the rest of the model learning, obviously. So there's a big shock and perplexity when you suddenly enable learning. So you'd want to do that on a ramp, but you can actually avoid that by simply having interspaced moments where the attention head is either on, or the attention head, or a modified version of the attention head is giving input to the MLP, which will better allow the MLP to not only understand the landscape, but it will also better understand its attention head slightly better, which reduces the shock when you do actually stop dreaming. And when you look at this pattern, it looks exactly like REM, NREM, recovery, sleep, wake.
I would try to test this by if there, like, in the brain there are one or more regions correlated with attention, and if that's less active while dreaming, I would say that's like some plus for this hypothesis, or more. Like, I would want such data personally. Yeah.
There are suggestions of this, but finding the actual cortical stack that simulates other humans has been done, but knowing whether it's enabled or not during specific phases of sleep is definitely too high resolution for us to do without invasive measures, which, guess what, would disrupt the system.
Yeah. It's hard to do ablations on humans.
Yeah, so that's why I'm thinking, silicon is a lot more forgiving, which is why I've been doing, if grokking is basically learning and thinking, which it very much looks like it does, because thinking and learning are all related to either memorizing facts or using those facts in a generalization. So if that directly connects, then you ask the question, what happens to a human or any biological system that is forced to not dream? We actually call that over-provisioning for AIs.
Okay. Interesting.
So there are analogs for both silicon substrate and biological substrate dreaming that are related to whether your attention head is on or off, or whether what your attention head is doing while transversing the landscape. Warm up is the most simple possible use of this that completely ignores all of the other hyperparameters, and I just continue to ask why.
Interesting. Okay.
So yeah, it's a theory, but also there are experiments that can be done, and I've done around 2,000 of them.
You can try to write it into some paper or something.
Oh, I have like 3 or 4 papers in my project, and I'm terrified to write them because what they lead to is concerning.
Oh.
When you add scale, things start getting really creepy.
I'll have to do some house chore for 5 minutes, so I'll be right back.
So yeah, not to take over, but this paper actually directly connects along with a bunch of other papers that kind of are coming at the same problem orthogonally. But if you really want to understand how these systems work, how these circuits work, the best lens to do that is really through grokking.
Yeah, I think grokking is also fundamental in many ways, but from different perspectives probably. I'll still be right back. I won't talk now for 5 minutes.
Yeah, no worries. I'm done. Sorry.
All good.
I was wondering that question actually. Why didn't they just use existing methods? They're up. It's different.
Well, the more novel the technique is, the less I trust the paper usually, because you need you have to pragmatically prove your method works usually.
Oh yeah. Got to start with the existing methods and then build methods based on those methods and make sure there are no confounds. That's fucking hard.
Or like at the very least compare it with existing methods.
Oh god, that feels like the bare minimum. Yeah, that's true. That's why I built a different method, because I couldn't interpret those operations.
Oh, I see. Was it for your grokking paper or this paper?
Actually, it was necessary for the grokking paper in order to identify a memorized piece of information and an actual circuit that does computation, because they both look the same to all current methods. So I basically said,
one.
okay, well, I expanded existing methods. I don't make anything. I'm a modder.
Yeah, but like, which papers gave techniques to do that, or was it in the grokking paper?
Oh, those were so all of that was based on the two papers that I already sent you.
I see. Yeah, I see. I'm not most familiar with grokking.
Yeah, so this is actually super. It's only the experiments and conclusions that I come to are really just combining those two papers along with some threads that they even mentioned in the papers that they just didn't pull on or that they didn't see. And as a systems engineer, I go, wait a second, why didn't you change this parameter and see what changed?
That's nice. So I assume your interpretation for engineers for why it's better, it's probably because like they use existing knowledge instead of trying to make a new unfounded knowledge, I assume.
I ground everything. Listen, I'm a systems engineer. I don't really give a shit about your theory. Like, theory is great for knowing like the best way to do things or the worst way to do things, but if it doesn't actually work and you can't prove it out to existing methods, then you're just fucking around.
Nice. I see. Your viewpoint's similar to like the Neil pragmatic interp and viewpoint.
Yeah, it's just that the main thing that they're missing is they don't have enough insanity. They need more chaos theory in order to be able to see things that they're missing. That's what I have. I'm a chaos goblin. I change hyperparameters simply for the fucking, just to see what happens.
Your exploration parameter is a lot higher, I assume.
Dramatically. But my grounding parameter is also just as high. They're actually locked. I got punished every single time that I didn't, because systems engineer. See, that is some shit. They're saying that the changes in hyperparameters don't mostly change the results. Yeah, okay. Based upon but that's based upon the way that they're analyzing their results. That's actually not based upon, that doesn't actually give grounding to their theory at all. This is one of the things I hate about machine learning papers, is that a lot of them are circular and they do it in really sneaky ways.
I think I didn't understand the reparameterization step.
Okay, I'm back. Reparameterization step?
Yeah, so they... Okay. So I was reading the thing, right? Okay, so reading the first questions, which is, why isn't the method operator LMs? Just explain a bit here.
Yeah, that's a good question.
Which is, yeah.
Exponential number of lines only after reparameterization step?
But the thing I was saying, so here they mentioned isn't the exponential size of the DRAS program, Probability problem, national number representation step, and I feel like I don't understand the representation step and what.
Isn't that just writing the attention and weights and embedding and so on, unembedding and so on, using the RASP formalism?
Yeah, but that doesn't give you an exponential number of. What is a line here, right? And what is the exponential number of them?
And
Figure
what
4.
scalable gradient-based approach are they using to prune them? What fucking hyperparameters are they using there?
They probably are doing the like they do take the gradient. I mean, they're
Check-
explaining more on the appendix, but I think they just take the gradient.
I think it's and I think it's explained in the theorem. No, I haven't checked the theorem yet though.
Yeah, that's the part that's hardest for me to read. Sorry.
Can you check the theorem, which is citing?
Which page?
Theorem 3.2. It's on page 4.
No, but the gradient part, I think, is just the typical thing people do on for this kind of circuit ablation, which is you take the gradient of the ablated part, change the ablated part with the output, and if it's 0, it means that it doesn't matter if you change it. Or if it's lower than some number, it's not going to be 0. But yeah.
Oh.
So it's like
I guess.
gradient approximation of,
Oh yeah.
But
Yeah,
people do the thing where you take all possible combinations of things and you delete each one and see if that changes the output. But that's too inefficient, so you use the gradient to approximate that. So it's like a linear approximation.
Yeah, I was just gonna say the only downside there is that I hope that their resolution is at least either at or close to the noise floor.
But anyway, so but Bernie was talking about the
Post token is input. Yeah, they in the Q&A they cite the theorem 3.2 on page 4 as leading to the exponential number of steps.
Yeah, but the theorem
Line.
says consider there is a DRAS program defining the same input map because in that. Okay, yeah, but they don't. Okay, so they prevent this appendix. So, maybe they probably should explain this on the paper if they are actually dividing in this way for the sake of the linear decomposition. But okay.
Yeah, you're right. They buried it in the appendix.
Yeah, so I understand. So let me. I'm going to turn on the lights in my room. Okay, so I'm back.
Yeah. What is H? H is the input number, right?
So they have a Let me read it. Sorry. Let the L number of numbers the layers on the transformer. H is the number of heads, right?
Number of heads. Okay.
So with a path.
Oh! I see. I think register stream in layer 1 can be represented in terms of 2 plus 2h plus 1 variables. So there's 2h. I think that's. No, it's still h. It's not exponential.
Wait, but is this all possible? A sequence over L multiplied by T? Isn't this all of the? Okay, so this is the combination of layers and heads, but this is just. I feel like we need an example. After asking.
Apparently, there's a full example of one-layer transformer in appendix figure 9. of this construction.
Okay,
So let's check
see
figure
that. Maybe
9.
it's easier to understand. I'll find some left.
Provided by this
Looking at
theorem.
this paper.
It's page 19.
Okay. I think the paper is cool. It's just very kind. One of those papers that is hard to understand. Maybe no.
If it's hard to understand,
easier way.
I can't judge it. No.
Okay, so as a summary for you, basically this is writing the transformers in this fancy way and then doing typical circuit ablations on them. But it has a cool step where they try to replace the activations with they try to replace the attention matrices with some pre-made ones and see what they and see if that works. And I feel like you don't need that like to make use of this whole RASP thing to do that. You could probably do something like that in a different way where you do the typical circular ablation things people do, but replace the you for example induction heads, you have some attention metrics as an induction head and you try that. I think that kind of works. Although maybe this is a more general way to do it with more math. Thinking about it. But I don't completely understand the like how the decomposition works and all that. It's having a really big decomposition and doing gradient-based things could work, actually. But, meh. I think this has the same problem that if you actually want to reverse engineer actual LLMs, you need other, like something that separates features to do ablation on them, because otherwise it's not tractable.
Maybe it could be combined somehow.
Yeah, no, if you had that, you could put it on here and it will work. I'm not sure. So the thing that this buys you supposedly is the attention, like the replacing the MLP via induction, well, the attention via induction head and all that, right? But and I'm not sure you need this whole RASP thing to do it. Maybe it is and it kind of works, but like maybe it's an overcomplicated version.
I feel like there's a simpler way.
Yeah. Alright, I don't think this one is that complicated. It's just explained very math person way. Like, because this is a few operations, I feel you could understand this with some actually better written guides of how they work, and then it will be intuitive. Like it's like a very simple programming languages. It will be intuitive how it works. I think if you understood it.
They're here. If you go right after this example, after pruning the beef 6, you have exact algorithm how to compute number of lines, and apparently the split MLPs indicates no, okay, somehow in this you have like the exponential rise, I think. So number of layers,
Okay, so the original token. Okay, so it is doing the thing, but I still, maybe it's with more layers, but I still don't get what the exponential number of lines is supposed to be, right?
Yeah, maybe.
I am going to ask Claude.
That's one option. I'm gonna do that. Exponential. Let's see what Claude thinks. The translation creates a separate variable for every path through the residual stream, and the number of paths grows exponentially with depth. That's why, apparently.
But what are the paths?
How variables multiply
After
layer by
the
layer.
problem is this all on the first layer, and they are not okay. So, Lloyd's.
Token, token, position, position, S1, S2, S3, S4. Each head produces k-squared selector terms. Every key query pairing of existing variables, plus k aggregate outputs. This gives roughly
You need to
k
ask
times
Glover
h
about this kind of thing.
new variables for that layer.
This is making
Oh,
me
I see.
realize the other person talking about the grokking paper made me realize how important the grokking paper is.
I don't know.
I never look at grokking too much, so I need to probably look
think
deeper into it.
I don't think it's that, or like I think in general the concept of models learn actual solutions instead of the memorizing is important.
I guess,
but
yeah.
I feel like generalization is important, but grokking seems like a specific example of it. I don't know how much that.
Yeah, it's also specific learning dynamics that get you to the generalizing solution.
But like, I buy it if he found a way to find it shows generalization for some parts.
It seems kind of vague, the thing. I don't know.
It's extremely interesting phenomenon to study, though.
Yeah, I mean, I think studying that kind of thing is interesting. I feel like maybe getting into grokking is not like thinking about the grokking specifically is not necessarily all of the.
No, I thought this was an interesting research direction. I probably need to look more into it.
Predictions of mass.
I want some generalization more generally. That was a nice sentence.
Predictions of mass.
I'm kind of surprised. Like the last time I talked to like my mentor Uze, when he thought when I told him my top K COT anchor idea, he thought it was like cursed. But then as I showed him more of the results, like he was more like pro. Like I remember talking to you before about that.
Okay, so the reason it's exponential is that
you see you have token and pose as two variables. So single attention heads creates 4 selectors. So that's already exponential.
Oh, and and after, but don't they aggregate after? Or
yeah, but they're still like their own lines, you know.
What is the output?
The aggregation uses them as a input. For 2-layer 2-head model, you go from 2 variables to 6. After layer 1 to 18. After layer 2. And the different variables have the program lines. Yeah, I guess that makes sense. Most of these paths are causally irrelevant. Which examples show the causal irrelevance? Yeah, they have token post. Figure 1.
Yeah, I still don't understand why.
The different programs have like different subset of this whole thing.
I think
So like
Claude
if you
was
go to
ironically also confused about the thing when the first time he explained it to me.
say again.
Claude was confused about the same thing as me. The first time I tried to explain and I asked a question, I didn't realize it was wrong.
Oh, I see. Okay. Yeah, you mean the exponential growth or something else?
Because
I
okay,
see.
so my question is, so Claude was saying the same thing as you initially, like the thing why is exponential here, but it does aggregation here, right? Shouldn't this turn it back into two things? So it not should be four.
I mean, by this logic, it would all collapse into M. No, it would all collapse into just 12th line. Because M includes A1, A2.
Yeah, and it will be one, and then but you still track tokens and token and positions separately after. But don't you? I need to see an example with 2 layers. Is the main thing?
Oh, I probably have to leave soon. I guess so. I didn't understand much of this one.
I mean, next time we are doing a paper that you should understand because it's about logic lens and you are the one who was interested. I didn't even heard about it. So.
Oh, you mean the tune logic lens?
Yes.
That was an elusive paper.
Oh, I mean, wait, no, sorry. I mean, we are doing the one that you said, like the scratch pad and the latest reasoning one.
The Scratchpad paper was cool, but like I didn't like
you
it turned.
Hopefully understand it, or at least be better to point. Have a better starting point to understand it from this week.
Yeah, I kind of confirmed the results. So like the results kind of were a little sus for
I'm also
Scratchpad.
having trouble understanding this one, right? I think I'm understand, but I spent a lot of work trying to understand it, and I'm getting tired. I'm asking Claude for help, and I think I understand it more or less. At least not all the details, but the gist of it. But still, it was not an easy paper to understand.
I see.
I noticed.
I
What did you say?
I think it's something is wrong with your internet. Or is it mine?
Or maybe he just disconnected now.
Classification task for me.
Oh, you now you weren't. We couldn't hear you for the past 10 seconds.
Oh no! I was just saying it feels similar, more similar to a binary classification for me.
This paper?
Like it's a yes or no.
Oh, I understand or I don't understand. I don't know. I think you spend a lot of time looking at the thing and trying to understand it. You eventually start understanding things. You might need to look terms and spend a lot of mental effort into it.
Yeah, I'm gonna spend a lot of mental effort on grokking since I keep on seeing grokking. It's everywhere.
I think the conclusion for the Neil paper is that it's not grokking itself is not that much of a big deal. Like it's an example of a bigger deal, which is in generalization. But yeah.
Yeah, many of the programs are just subsets of the whole decompiled structure. That's very interesting, though, that you can that this is general enough to define. Can you do that element-wise operation? Yeah, that this decompilation is general enough to define sort, unique copy, etc., most frequent.
Is there any example of any two-layer model?
Yeah, I don't know. Maybe Claude will know.
Oh, maybe here.
Are you guys
Alright,
using
okay, so
Claude to like
there are some
understand the
examples
papers?
with more than one layer, but they are already pruned, right? So I'm curious what the whole thing is.
Victor Verdi, how much you use Claude to understand papers?
I didn't used to do that, but I feel like the last 2 or 3 papers I noticed that it's actually very useful. I should be using it more, but I basically haven't been using it before now.
As long as you double
Isn't it a
check
bad thing to
what
use
Claude
Claude
is.
to understand papers because that's like gonna make it so like you're relying on Claude?
Oh, also, yeah, be very careful with that. I don't think you should do it if you, especially. I think you probably shouldn't do it.
I do not want to develop. I'm trying to avoid a Claude reliance at all costs. But
I think it can be useful, but you have to be very careful to not have it generate bullshit.
Yeah, as long as you like ground, as in the equations and words it says are in the paper,
Yeah.
or somehow derived from it.
And you have to be very on the mindset of, is this bullshit?
Yeah. Claude often says stuff that's bullshit. You have to be mindful of that.
well, the training data included a lot of that too.
Yeah. Sometimes when you take the rate, sometimes I'm thinking that the rate of bullshit that Claude says is smaller than the average population, but whatever. There are different
I think Grok
kinds.
actually improves Twitter discourse. Sometimes.
Yeah, that's funny. Like how people are trying to argue with Grok to agree with them, but Grok is pushing back constantly.
Yeah,
and
that's
they're
actually
saying bullshit
nice. I'm
sometimes.
surprised the web Grok does that. I think it's also because there is multiple people, and the web Grok tends to agree with the first person it talks to.
Does Grok agree with anything you said Elon agrees with?
Actually, yeah, well, I think Grok is generally reasonable, except the topics Elon was sensitive about recently.
Yeah.
I think that's...
Also, I've seen some people claim this is only because of the prompt, like the system prompt, and I think there's some, maybe I don't know if there's an API or something, but there is some way of changing that.
You're saying Grok weird.
Say again, you were cutting off.
I'm not hearing you if you're talking right now.
Is it just the system prompt? Me?
We-
Oh,
Oh,
can
Now
I
we
hear
can
me?
hear you.
So,
now we can hear you.
yeah, is it not the system prompt? Is it not the system prompt? So you're saying that grok is normal and reasonable? It's just the system prompt?
I don't know. I think some people claiming that. I don't think it's completely true. I think Grok also tests some in some tests it's at times weird. But I think I wouldn't surprise me in part of it is in fact there is something on the system prompt about it. You should agree with Elon Musk or something.
Yeah, no, well, there's also source prioritization, and the first sources for a lot of questions that Elon is sensitive about are the first sources are Elon Musk, basically.
They probably do some fine tuning on it for that, but it's hard to. People were talking about it's hard to get the model to be actually, to have a model that is a useful assistant, but is still, quote, not woke.
Reinforcement learning with Elon feedback.
They accidentally keep trying to make it agree with Elon. It only ends up doing really weird things, and when it talks about Elon, and then not really agreeing with everything else.
Yeah.
It's not aligned with. They can't align the grok with Elon.
They have to solve the
Well,
alignment
you
problem
have to.
first, which is an issue.
You need Elon feedback. You need Elon feedback. Elon is secretly the. You see, like we all have to be servants of Elon. That's what grok wants.
Mm-hmm.
Oh, because
Yeah, this paper is so
okay,
long.
I understand. I think, or well, I don't know if I understand. Claude has an idea that might make sense. But
Understood.
I would want. So Claude claims it decomposes like this, right? Sorry. So, and here it will be exponential because you still have the position, like you have skip corrections, so you still have all possible variables, right? So you. Yeah, so basically that's why you get this exponential thing, because you have to take all possible inputs, so, and your input is always all of the... This shouldn't be as big. I feel like it's still missing the aggregation step. Something. So did Rembert left, or who did left?
Probably internet.
Okay. I mean, I think I'm kind of tired. I'm probably going to leave it here.
Yeah.
I still don't understand it fully, like how they divide the model. I understand most of the other rest of the paper. Like I understand, I will have to. There is a feel like there is a lot of cool things to see on how the examples for algorithms works. And these are, even if they did in the right, this is a cool example of toy model decomposition. And I could probably spend a lot of time understanding it in them. But yeah,
like it makes sense to me. I don't know if like here, like there are various patterns in the matrices. I think you don't really need a RASP formalism, and you could just have some like library of like these circuits that are like.
I feel like I think that's true, but I feel like the way the RASP thing works, the library will also be almost equivalent to the RASP thing.
I see what you mean.
Like if you imagine some attention matrix, that's just going to be the same as a this is just in some sense it's just a fancy notation for something like that.
Yeah, but I like this.
Yeah. And you could, I think you probably will write it in a way that computer programmers understand better than this fancy notation. But at the same time, this fancy notation also lets you do interesting things about formalization and doing math stuff of proving things with it and all that. But yeah.
and
Yeah.
it's
I
probably
see.
also related to
These
previous
are
literature on RASP. But yeah.
Yeah, these are all the tasks, or some of them.
Also, okay, so it's interesting that there are a lot of them for which the
Linear norm.
yeah, the layer norm actually does things.
Oh yeah, I see. Yeah, that makes
There's a bunch
sense.
of things that could be their own papers.
Yeah, for sure. This is a very big paper. Yeah.
Method imagine for multi-input MLP. Okay. Diagonal matrix. So also there is no matrix for there is no single matrix for induction heads actually. Like induction heads, this is not new. You make them with two, like more than one layer. Like you make them with two attention patterns.
Yeah.
Like on this example.
I think here they just show the like the line 3 still needs like A1.
Yes, but I mean this. Yeah, but this is what. So basically, the induction, right, is k equals q minus 1 and k equals q, right?
Yeah.
I mean, this is always when you see induction heads for transformers. This actually this usually this thing where you have two heads on one head on a previous layer that does this thing, and another head on the next layer that does this thing. On my paper, where I reverse engineer a model, there was also something like this.
I see. Yeah, the line 3 takes the k equals q and the S1. Yeah.
Yeah.
A1.
I think I'm going to stop the recording of that.
Yeah. Yeah, I might or might not go more to this example and then try to look more